All right, let's sit down. Then we can continue. We will finish by 3:50. All right, so just 45 minutes. Okay, so we think that the challenge is in learning how to scale up electrified production systems, right? And this is because if I show you this slide, right? So this is a logarithmic plot. I don't know if you can see it from the back, right? This is 100, 1,000, 10,000, so one order of magnitude. This is the energy consumption or generation in watts. And this is the CO2 emissions per ton. In tons of CO2 equivalent per year, right? So someone in LA, right? As a whole, LA, we produce around 100 million tons of CO2. Each person, each one of you per year is responsible for 10 tons of CO2 because we're 10 million, right? And your average energy consumption is around 3 kilowatts, right? This is where one person is here, right? A rooftop solar system generates in average 10 kilowatts or so. Okay, so 10 kilowatts, that means that it generates enough electricity for a family of 4 or 5. All right. This is a typical rooftop solar. The largest solar plant that is in Nevada, I think, is the Solar Star. At least it was the largest a couple of years ago. That generates around 500 megawatts, a little bit high, 600 megawatts. So it's getting to 1 gigawatt, similar to one nuclear reactor. Okay, that's one solar power plant. Right? So this is a big area. We have a power plant at UCLA. Have you seen the UCLA power plant? It's a cogeneration plant, so you use natural gas. It's next to the hospital. All right. So have you seen the emergency entrance? Now the road is actually blocked because they are changing a revoid or something. All right. So that's in front of the UCLA power plant. It generates around 60 megawatts. Okay, so that power plant, 10 of those power plants is equivalent to the largest solar plant that we have right now. In LA, again, we're 10 million people. We consume energy at a rate of 34 gigawatts, and we produce 100 million tons of CO2 equivalent per year. The US, we're 328 million people, right? And then we generate almost 4 gigatons. The whole world generates around 30 gigatons of CO2 equivalent per year, 30 to 40. So what you can see is that our energy consumption or our energy generation is obviously linked with the CO2 emissions, right? Most CO2 electrolyzers, right, that can take CO2, water, and electrons, right, are somewhere here. All right, so this is actually lab scale. This is where most of the materials, most of the development, all the news, all the solutions that have changed the world already are operating at this scale. Right? This is where all the papers are showing up. Very few papers, maybe one that is at 1 kilowatt price. In our group, we're trying to push a little bit and see if we can make something larger in the next few years, right? Why? Because unless you're able to get in 10, 20 years somewhere here, right, there is no chance that we will be able to take CO2 at a large scale and make fuels and chemicals, as I was showing before, all right? So we think that the problem is scale up, all right? How do you make things 10 times larger, 100 times larger, 1 million times larger, right? 100, 1,000 million, 1 billion, right? So these are actually 12 orders of magnitude. So it's a big task, right? So in our group, at least, we recognize that the challenge is that there are no fundamental principles on how to scale up electrocatalytic systems. And we think that that is simply because there is an implicit complexity in these systems, right? So you have materials, you have mass, heat, charge transfer phenomena, right? So these systems actually get very, very complicated, all right? And to actually be able to scale up those things, right, you need to be very good at taking fundamental knowledge, right, and applying, right? And for that, I think at least that even the best students that we have, right, they will not be able, I mean, they can capture the complexity of a reactor that you have in front of your eyes, right? But how to scale up or how that will look 1,000 times larger is something that is extremely complicated, right? So a lot of the efforts in our lab is in actually using or leveraging machine learning, artificial intelligence, right, teaching computers how to think, how to design, right? Build models that are predictive, right? So to see if you can actually go faster from fundamental understanding to applied research, okay? I don't think a student or the best engineer will not be able to imagine or build something out of the blue, right? I think the only way is to teach computers probably to close that gap. We also use a lot of dimensionless analysis. Okay. If you're a chemical engineer, probably you learn dimensional analysis, right? And you also learn about these processes, right, of scale up and scale down, right? So many times, if you ever work in a refinery, right, you actually have big reactors or complete distillation columns, right? And you're trying to understand maybe because something is going wrong, right? What to do. And the reality is that you cannot do experiments at that scale. So you actually need to scale down, right? And so if you're able to scale down, most likely you're also able to scale up, all right? But how to do at a smaller scale something that is representative of a large system is something that chemical engineers are trained to do, right? So when we talk about scale up, this is not scale up, right? So scale up is not that you have a small electrolyzer and then you just multiply all the dimensions by 1,000,000 and then you solve the problem, right? So there are a few problems it says here, right? There are a few problems going from lab scale to full scale commercial, right? And what they have done is just taken typical beakers, right, that you use and you just blow them up, right? That's not how scale up works, right? So we use a lot of dimensional analysis as a scale up tool. Okay, dimensional analysis, there is no length, no mass, and no time. Because there is no scale, there is no scale up problem. All right. So scale up then is simple, simply express the process using a complete set of dimensionless numbers and try to match them at various scales. So many times when we have a batch reactor, at least in chemical engineering, we know that you can actually come with a power dissipation number, for example. You have an idea of the stirrer, what are the rotations, the hydrodynamics, viscosity, whatnot, right? And you can come with a power dissipation number. And if you want to scale up that process, right, you will try to match that power dissipation, but that the reactor might look completely different. The stirring rates might look completely different, right? The mixer that you use. So scale up or dimensional analysis, essentially what you're saying is my optimal catalyst, right, or electrochemical system operates when this parameter that I have decided that is the dam color number is 1. Okay, and so then what you try to do is get 1 in terms of dam color number at all the scales that you scale up the process. The system might look completely different, all right? But when you go and calculate that dam color number, that should be 1, all right? So probably you have heard about Reynolds number. Who has learned about, even if you're not a chemist, maybe mechanical engineering, you guys learn Reynolds, right? All right. The Reynolds number is a ratio between inertial force and viscous force. Okay. Nusselt number. Right. Where do we use Nusselt numbers? For heat transfer, right? A lot. All right. So then the Nusselt number is just the ratio between the convective heat transfer rate and the conduction heat transfer rate. Right. Dam color number. Right.
Yeah,
Right. So it's the dimensionless number that tells you what is the relation between a reaction rate and a convective mass transport rate. So you imagine that you have a catalyst or a surface, an electrode, all right? That electrode can do a transformation, all right? But you're trying to bring hydrogen in a fuel cell, right? So the hydrogen needs to get to your platinum catalyst, right? The question is how fast is the hydrogen getting to your catalyst and how fast is the catalyst reacting that hydrogen, right? That ratio you can actually calculate. And that will give you a dimensionless dam color number, all right? Okay. Sherwood number. And so these are the definitions of many of those terms. Okay. The Schmidt number is the ratio between viscosity, density, and diffusion coefficient, all right? We use a lot of dimensionless numbers, right? Because sometimes we change the temperature or in any electrolyzer, the temperature starts to change. As the temperature changes, right? the viscosity changes, the density maybe of your liquid changes, the diffusion coefficient changes. Right? If you're going to simulate a complex system, you will have to write the correct equation for each one of those terms, right? So actually using dimensionless number is a way that is simplified. You decrease the number of variables in your problem, right? So you have a reduced order problem when you actually use dimensionless numbers, right? So the Schmidt number actually captures those changes in those different properties, right? So if your name was given to a number, probably it means that it's a very important number, all right? Essentially, take it like that. Yeah. All right, so there is a few of those dimensionless numbers, and I don't think that we're making new ones, all right? So they are extremely powerful, all right? But you will be surprised that they are not used in most electrochemical books, only maybe in this one you will find dimensionless numbers. This one you will not find dimensionless numbers. Another. All right. Okay. So we look a lot at the num-color numbers. Okay. Why do we care about these systems, right? Imagine that you have a flux of CO2. So you have CO2 that is coming from the gas phase, right? You have a gas-liquid interface. So the CO2 is going from the gas to the liquid. In the liquid, you have some capture agent, for example, an amine. You actually make carbamates, bicarbonate, different things, right? In the bulk of the liquid, right? And then you're trying to bring that CO2 or carbamate to the surface of an electrode to do a reaction, okay? So what happens is that you actually have all these different variables. You have the partial pressure of CO2, the flow of CO2, the temperature of the liquid, the concentration of the MEA, the monoethanolamine, the capture agent, the concentration of hydroxyls, the applied potential mechanical forces, and reaction rates, right? The reality is that from this, so these are the variables of the process, right? And you have dependent variables that are the diffusion coefficient, density, things that you can describe with, you can find in books, right? In tables. All right. The reality is that all these dimensionless numbers are made out of these units. Okay, so you can see how you can actually start to reduce the complexity of your problem, right? If you have the Reynolds number, the Schmidt number, the Hatta number. What is the Hatta number? If you're a chemical engineer, the Hatta number, Hatta. Do you learn? It's for the enhancement factor for absorption of CO2, for example. If you're absorbing CO2 in water, okay, if you put in that water some hydroxyl or some MEA or some capture agent, right? Because now you have reaction of CO2 with that capture agent, you're actually accelerating the absorption rate because you're not limited by equilibrium of CO2 and dissolved CO2 because you react that CO2 further, right? That's a number data. It's called Hatta number. It's an enhancement factor, right, for absorption. Anyway. And then from the damn color number, you can get to conversions and selectivity, all right? So we're interested in using dimensionless groups simply because then you can reduce the complexity of the system that you have. And you will see in some of the books that you start to use more and more dimensionless numbers. Okay. So I studied chemical engineering. I learned all these things during my undergrad. I never used them during my PhD or postdoc. All right. And now I try to use them every day. Okay, now I feel like an engineer because I can use them a little bit. All right. So these are extremely powerful. You learn them not only in chemical engineering, you learn in materials, I'm sure in mechanical engineering, you learn it. Material science, probably you have learned some of this. All right. Very powerful, okay? For all purposes in this class. All right. So also something that we do a lot in our lab is we look at, we have a smart manufacturing inspired approach to scale up things, all right? So maybe if you do any type of research, right? Maybe this is how you look at the problem. So here, the physical device, we put it as a CO2 electrolyzer. You can imagine maybe it's a battery or something like that. typically you have sensors, right? If you have done experiments with a battery, what are the sensors that you have? If you have you ever, someone has cycled a battery of research? Yeah. So what sensors do you have?
Like a thermostat for the.
Right. What else? Maybe a thermocouple to measure temperature, right? Yeah. So those are the sensors, right? And the sensors are between your physical device and some data, right? So you use sensors to extract data, right? All right. So imagine there is not a CO2 electrolyzer. Imagine there is a baby. All right. So you can have a thermometer, right? And that will be your sensor, and you will get some data. All right. So maybe it tells you 96 Fahrenheit. Maybe it tells you 100, 104. So what does it mean? The number in itself, it will not mean a lot, right? Unless you have some models, right? Maybe many people did experiments with measuring the temperature of healthy persons and someone that were sick, right? And then they recognize that they extract a lot of data and they created a model that says, we have an insight that if your temperature is 104 centigrade Fahrenheit, right, you will get sick. If you're 96, most likely you're healthy, right? So they generated insight by having some sort of model, right? And they generated a lot of data, right? Also, in electrochemistry, many times we try to do control, right? So what that means is that we try to, out of that data, go and optimize the electrolyzer, right? If you go back to example of the heat, right, maybe you will give some medicine or something, right? The reality is that we look at the problems a little bit more complex, all right? The reality is that you have your physical unit, right? You have your sensors. What we're trying to do is generate a lot of big data first. Right? So we have the electrolyzers, we change the temperature, the pressure, the hydrodynamics, the concentration of species, right? Try to identify what are the variables that are actually relevant to many of the processes that we have. That data doesn't make a lot of sense unless you contextualize it, right? And once you contextualize that data, is that you actually extract information, all right? If you go back to the example of healthy person or not healthy person by measuring the temperature, right? Let's say that you, as contextualization, in the big data, you will also say, you will measure the temperature, but also say, is that person coming out of a sauna? So what is the context? First, temperature measured 99. What is the context of that 90? And then you can extract information, right? Once you have enough information, you can do actually analytics. Right? And from the analytics, you can get some insight. And it's the same in the electrolyzer, in any of those systems. Right? And then is that we actually do modeling, right? So we extract a lot of data and we actually determine what are the variables that are actually important for any model that you have, you're going to build. In this case, right, in the simple approach that we have, many times you will see that people in your field end up modeling things that are irrelevant. All right. It's simply because they're trying to feed the data and make a story out of this, right? So you will have some data, you will make some models, right? And you will claim that to have some insight, right? But the reality is that maybe the variables that you're measuring are not that relevant, right? So modeling is the last thing that we do once we actually have a lot of insights, right? And then from modeling, we extract some intelligence, right? And from that intelligence is that actually we try to do control. So we learn as chemical engineers at least, right, that, and I'm sure in electrical engineering, right, unless you have the right model, right, for a system, right, you will not be able to control signals, right? So when you demonstrate control, that means that you have some mathematical function that actually describes the main processes that are happening. Not that it needs to have all the complexity or capture everything, right? But if you can actually control something, that actually means that you have some level of understanding of what is actually happening. So in our papers, a lot of efforts are in control, right? Because control, we see it as a demonstration of actually having an understanding of what is going on, right? We, as control, we also do design and scale up, right? So if you can describe mathematically a function or a system, right? Then most likely you can have a better idea of how to scale it up, right? And then the question is that correct or not? And then we build something that is larger, and then we just go back in these circles, right? So that figure from the right actually comes from smart manufacturing. Okay, so that's what we call it, a smart manufacturing approach. So they use this type of approach to describe production lines, manufacturing sites, right? So they try to build essentially a digital twin. Okay, a digital twin means that you actually have a model of the complete process, right? Okay. All right. So why are we interested in CO2 electrochemistry, right? What happens with CO2 electrochemistry? It's really a lot of reactions, right? So you can take CO2, water, and electrons, and you can make all sorts of products. So we have hydrogen, formate acetate. We're interested in making ethanol. Ethanol, you actually require the making and breaking of more than 12 bonds, okay, to make ethanol from CO2. So what happens is that in that process, you can actually end up going to different products, right? So you can imagine that this is the complexity of the reaction network used to take CO2, water, and electrons to make ethanol, right? So probably if you do 5, 10 experiments, right, you will actually not be able to capture the complexity of this process. Right? So we always think that to understand and control a complex reaction like this one, you actually require a large and complex data set. Right? This is like if you need to decide where to go for graduate studies, right? So probably you will not just look at one university and say there, right? So you will try to collect a lot of data, right? The more complex the decision that you need to make, the more data that you will try to collect, all right? So for that, again, for the complexity of the systems that we're trying to scale up in electrochemistry, you most likely need to have a big data set. So automation and artificial intelligence is very important. All right. So maybe a little bit more specific to what we do in our group, right? So if we're trying to transform CO2, right? This is the classical view of a reaction transfer process in heterogeneous catalysis. And this is the same thing that we will see in the electrochemistry book, right? So you have, let me just stop here and say, this looks chemical engineering heavy, but it's not, all right? You can find parallels for everything, all right? You can have, in bio applications, maybe you have, imagine that it's not a CO2 molecule, but it's something that is in the bloodstream, if you want, and needs to go through a cell wall or something like that, right? So imagine that you have a molecule that has to transfer across different phases. Here in this case, we're using CO2. We have to go from the gas phase to the liquid phase. We know how to describe the transfer, right? Maybe that molecule will move through some liquid layer. It will go into some porous catalyst, right? And it will react inside of that pore. And then you have all these 12 different steps that can happen all over that catalyst, right? And then you make a product, and that product needs to come out. If you want to think of a biological process, imagine that that's your drug, right? You're making it go through different tissues, right? And eventually it gets to the place where you need to activate it, right? And then maybe you need some other molecules that need to come also at the same time. Not a bio person, so I'm not offering medical advice or anything, right? All right, but anyway, in catalysis, many of these reactions are endothermic or exothermic, right? So that means that heat transfer also needs to follow a similar track. Many of these reactions require heat, so the heat will come from the outside. Some of these reactions in a fuel cell is an exothermic reaction. So you actually need to release that heat and dissipate that heat, right? A lot of the efficiency of fuel cells is linked to with heat release, right? How fast can you release that heat that is being generated in the fuel cell? And if you have an electrochemical system, then you have ions, all right? You have electric fields, you have a lot of different things, all right? So it's a very complex process. And that's why we will take you one of these Fridays to see our experimental setup, right? So we have this type of electrochemical cells that we can control transport. And what we have done is done a lot of automation of the potential stack. So the potential stack, everything is digitalized. We also have gas chromatograms, so we can analyze gases, right, in real time. So everything, it's what we have done is taken that smart manufacturing approach, right, and map it specifically to our problem, right? And essentially, you can borrow that part from the top thing. That's what we did, right? The yellow things and the blue things, and you can actually apply it to any problem that you have there.
The CO2R is harvest reduction.
CO2 reduction.
Okay.
Yes. Sorry. Okay. But I will argue that you can actually take those yellow, the words in yellow and the words in blue and apply it to any problem that you have in doing your PhD. All right. So you can actually have, if you look at your unit, whatever it is, as a system, right? You probably have sensors that generate data. If you do modeling, right? Try to work with someone that does experiments, right? To actually understand how is it that data is collected. All right. So many times I think that that's the issue for people that do modeling, that they don't actually know how the data is extracted, right? And there might be already a lot of problems there. So again, think of the sensors, right? In our case, we have gas chromatograms, NMRs, a potential stat, right? Mass flow controllers, different things. We collect big data, like GC data, currents, potentials, right? We use machine learning-based product quantification, so we can, for example, relate production rates of different products to different operating environments. Okay, and from there we can actually start to generate these sort of maps between outputs of the system, that would be the production rate of different products, right, and the inputs, that would be the potential, the current, the hydrodynamics, the temperature. We try to build a multi-scale model, right? So because these processes occur on multiple scales, and we are trying to make this multi-scale model eventually to be predictive. All right, so that means that you actually need to go back, do some multi-scale model, have some prediction of what the reactor should operate in conditions that you haven't done it, right? See if that actually happens. If it happens, then good. If it doesn't happen, then you have to go back, right, and improve your multi-scale model. Eventually, if this multi-scale model is not predictive, I think for us it will be very difficult to rationally design larger scale electrical process. That's right. But again, I will argue that you can take those words in the top and you can apply them to any master project that they give you or PhD project, right? All right. So we didn't invent smart manufacturing, we're just borrowing that approach. Okay. So some of the reactors that we make in our lab look like this, right? So it's gas side. We can flow gases. We can provide some reactants to this is the electrode. Okay, so imagine CO2 comes, that's a copper surface, and then that CO2 starts to break apart on the surface of that copper and starts to make different products. So what we do is that we can actually control the hydrodynamics in that system. Let's see if it. Oh, it's not a video. Okay. This one.
Exit the presentation.
Let me see. No, I think it's maybe it's actually loading, but it was. Anyway, so this is the next slide. I will use a CFP. Let's see if I can go. What is the presentation modes?
We use ANSYS Fluent for the.
Yeah, this is with ANSYS Fluent. Yeah. All right. This is just a recording of the cannot play media. All right. What is this one? Okay. All right. Later I will show you. Next time. So anyway, we can simulate the hydrodynamics of the system. At a reactor scale. So we also do a lot of let's give it a second. All right. So we do a lot of correlations between inputs and outputs. All right. So what we do is essentially correlate products with potential rotations, with current, and other variables in the system. All right. Later, next time I will show you this. All right, and what we do is just look at multi-input, multi-output conditions, right? So we change a variable, we see how the product distribution changes in our reactors, right? We try to understand what are the parameters that are important, what happens if we increase the potential, what happens if we increase the hydrodynamics. So this is the Sherwood number. So this is just related to the rotation of the cylinder. What happens if we improve transport, right? Use transport seems to change the selectivity of the systems. What happens if we change the electrolyte concentration? Okay. Yeah. So we look, all this is experimental data. All right. So we just take the same catalyst and test it 300 times and see under different conditions, not the same conditions. So we try to map out all the conditions that are relevant to the process, and then use that information, build a model, and try to scale up the units. Change the temperature, we change the porosity of the catalyst, change many things. All right. The last 10 minutes, I will talk briefly about water and energy. Okay. Any questions so far? No? Feel free to ask anything. So water, right? This is the distribution of water in the different regions, right? Turns out that this is the only fresh water that we have, right? So it's around 2%. And so the one that is accessible is actually much more limited, right? There's a lot of fresh water in ice caps and ice. As the iceberg is forming, right, it starts to push out the water and makes the water structure and ends up just pushing the salt outside, right? Anyway, in California, if you live here in LA, we actually get a lot of our water from North California. Okay. I think in the last year or last 2 years, there was enough rain that we actually accumulated enough groundwater to last a couple of months or something like that, or a year at least. Okay. So when we have a lot of rains, it actually goes through the ground and underground, and that help us with. And we also get water from the Colorado River. Okay. So here in LA, 2/3 of the water are imported, and 1/3 is actually from local supply.
What's it out of states?
From North California.
So it's
Yeah. All right. So this is typically what our water demands, what it looks like, right? So actually, a lot of the water is actually used as cooling water in industry, right? So industry uses a lot of cooling water. Industry itself uses water, and the amount of water that enters the public water supply in average is just around 14%. And out of that 14%, 60% goes to households and small business, right? Some of them goes to applications in industry, and then there are a lot of water losses, right? Okay. So this is just to say, water is actually a scarce resource. This is just a map that tells you, or the table here on the left, it shows you the domestic water use in gallons per day per person for different countries, right? You can see that the US in average is between 80 and 100 gallons of water per day per person. This is the total water consumption divided by the population. All right. So in developing countries, let me see if it's there, right? Developing countries, right? The average is around 5 to 7 gallons per per day per person. And this is the average British person's consumption in the 19th century. Okay? So you can imagine that the people that are living in developing countries their water consumption is much less, but that doesn't mean that their demand is less, right? It's just because of availability. All right. This is how much water we actually use in liters to generate a unit of these products here on the left, right? Probably you have heard, right, that textiles, making cotton actually requires a lot of water, not only in the growing of the cotton, but also in the processing. All right. To make aluminum, right, you need around 1,000 liters to make 1 kilogram of aluminum, right? That's why we recycle a lot of the aluminum cans, right? Consumes a lot of energy and a lot of water. But it's easy to recycle metals. So these slides, you have them, right? So I would recommend that you look at them, right? See how much water is used to make a pint of water here. Fine. Okay, or coffee. Right. And now there is seawater desalination. Someone is thinking of water, treatment of water or desalination? No. Right. Okay. Right. Some of the principles are similar, right, to this, but this is a nice paper, right, that summarizes developments in desalination technologies, right? And what you can see is that this is the energy consumption for the different steps that you have. You actually have seawater intake, it would be this one, right? So you need pumps, you need to move that water to some height or something, right? Then you need to do pre-treatment, okay? So typically from seawater, you try to remove some of those components, right? By physical or chemical means. And then the component that occupies or uses the most energy is reverse osmosis. Have you heard about reverse osmosis? Okay. So you use what is the driving force to purify water there? Pressure. Right? So you try to have a big pressure drop across the membrane. And then obviously you have the post-treatment, right, of those brines. So this is how the power consumption has been decreasing, right, over the last 50 years. Right? So this dashed line is the theoretical minimum, right? And we're almost close here to around theoretical minimum, I think it's 500 watt-hour per cubic meter, right? And we're getting very close, right? So the more salt that you have, that figure, what it tells you is the more salt that you have, the more energy that you will need, right? And then also the more recovery that you want to make from that water, the more energy that you will have to input, right? Okay, so if we want to use plenty of water that we have from the ocean, right? This is just telling you that you also need plenty of energy, right? It's not free. Okay. This is just telling you that there is a relation between water purity, and energy. Okay. Then there is also the water used by power plants, right? You might be surprised, but nuclear power plants is a lot of water. Coal also uses a lot of water. Solar thermal also with wet cooling also uses a lot, right? When you come to natural gas and solar photovoltaics, then this water starts to decrease. Still, you need to clean those panels, right? You need to do some of the services that consume water. In solar thermal with dry cooling requires less. In wind, during operation, it consumes obviously much less. So this is telling you that we consume a lot of water, right, used to produce electricity. And then this, I don't think that I need to explain too much, but there is obviously a link between water, energy, and the environment, right? This is something that has been proposed, right? That you can have, or this is actually how industries operate, right? So you have crude oil, natural gas. We can do actually gasification to make syngas, carbon monoxide, and hydrogen. And from there, we can do all these type of chemicals, right? There is some chemistry that is called Fischer-Tropsch, where you just start to make a lot of longer hydrocarbons, and from there you can do gasoline if you want. Right. Right. This is just significant emitters of CO2, how CO2 concentration has been changing. Right. And I will just end with the next 2 or 3 slides, right? So today we consume energy at a rate of 18 terawatts with 80%. This is sort of a summary of the discussion today, right? 80%, so more than 14 terawatts coming from fossil sources, right? By the year 2050, we estimate that we will require around 20 to 30 terawatts of energy supply. Why do we think that this will increase, this number? Because of population, right? AI, different uses, right? And also, as developing countries start to come a little bit out of poverty, right? They will also increase their energy demand, right? It will not double, even if the population double, because we think that we will improve our efficiency. Okay, so efficiency is also included in this analysis. So it means that, we expect that to be CO2 emissions free if we want to reach a 2-degree warming cap, right? So then the question is how to get that much carbon-free energy, right? And that's something that we will discuss in the beginning of the class on Wednesday, right? So today, on Wednesday, slides, so big picture, right? And then next week, we will change to more of just writing the board and taking notes, right? But just give me the last time, if I want you to remember something, is that the global energy, what is the global energy consumption and the landscape? Remember that energy is precious, that water is precious, and that we need to do a rational use of energy, okay? All right. Thank you. You need a PTE. I can generate PTEs now here. What is your UID?
I emailed.
If you have it.
Yeah, I have. 406 354 192. You found me? My name. I am not registered with it asks me to go.
Is this the right UID? 406
354 192. Yes. But I'm not in the waiting list.
No, I know.
Because I have to.
Let me. Cannot generate, but I will look at your email and we'll make it again. I will reply to your email. Questions outside? Yeah, you can.